Part 1, Introduction to Black Holes Formation. Consider a red supergiant star, perhaps 20 times the mass of our Sun. These colossal stars are among the largest in the universe, with diameters that can span hundreds of times that of our Sun. This star has reached the end of its life cycle, having exhausted the hydrogen fuel in its core. As it ages, it begins to burn through its helium and other heavier elements in a desperate attempt to sustain itself. Over millions of years it has burned through heavier elements, culminating in a core dominated by iron. This process creates a layered structure within the star, with each layer burning a different element. But iron is unique. It doesn't generate energy through fusion. Instead, it acts as a dead end for the star's nuclear processes, leading to an inevitable fate. When the core's mass exceeds the Chandrasekhar limit, about 1.4 times the mass of the Sun, it can no longer support itself against gravitational collapse. This triggers a catastrophic implosion, marking the dramatic end of the red supergiant's life. As the core collapses, protons and electrons are crushed together to form neutrons, releasing a flood of neutrinos. This process happens in a fraction of a second, yet it is one of the most energetic events in the universe. The neutrinos, almost massless particles, carry away a significant portion of the energy, allowing the core to cool and contract even further. The density skyrockets to around 10 to the power of 17 kilograms per cubic meter, comparable to that of an atomic nucleus. This extreme density means that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. The core's density is so high that it warps the fabric of space-time around it. The outer layers of the star, no longer supported by the core, are violently ejected in a supernova explosion, a blast so powerful that it outshines entire galaxies. This explosion not only creates a spectacular light show, but also disperses heavy elements into space, seeding future generations of stars and planets. What remains is a neutron star, if the core's mass is below about 3 solar masses. These neutron stars are incredibly dense and have strong magnetic fields. They can spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. However, if the core's mass exceeds this threshold, neutron degeneracy pressure, the quantum mechanical force that resists further collapse, fails. This pressure is a result of the Pauli exclusion principle, which states that no two neutrons can occupy the same quantum state simultaneously. The core continues to collapse and gravity becomes so overwhelming that the escape velocity at the surface exceeds the speed of light. At this point, a black hole is formed, an object with a gravitational pull so strong that not even light can escape from it, marking the end of the star's life cycle. At this critical stage, the core of the supergiant star contracts dramatically into what is known as a singularity, a point where matter is compressed to an almost unimaginable infinite density, and the curvature of space-time becomes infinite. This process is both violent and awe-inspiring, marking the end of the star's life cycle. Surrounding this singularity is the event horizon, a crucial boundary where the escape velocity equals the speed of light. Beyond this point, nothing can escape the gravitational pull, not even light itself, making it invisible to the outside universe. This marks the birth of a black hole, a region in space where gravity is so intense that it warps space-time itself. The gravitational field is so powerful that it pulls everything inward, and nothing, not even light, can escape its grasp, making it one of the most mysterious and fascinating phenomena in the universe. The formation of a black hole is one of the most extreme and fascinating processes in the universe, transforming the remnants of a massive star into an object where the known laws of physics break down.